Hello again. Still on the topic of trigonometric ratios for this lesson. We've done one lesson already, which has revisited the sine and cosine rule. Today we're going to have a look at what I call the ambiguous case of the sine rule. In the sine rule, we might sometimes be finding an angle which is acute or obtuse. How do you know if the angle you've found is actually the right one? We're going to see later that sometimes with the sine rule, in some cases, the angle you find might actually be acute or obtuse, depending on the question, which can be confusing, which is why we have this lesson to try and clarify it. But before we do that, there are some warm-up questions. I've only got 3 today. Here they are. So attempt these first, pause the video now, and when you're ready to see the solutions, press play and double check your answers against mine. So let's have a look now at question 1. Question 1, we're just trying to find out for the 4 triangles if to solve them you'd use the cosine rule, the sine rule, either or neither to find x. So some cases we could actually use both, some cases it's one or the other, and sometimes the sine and the cosine rule neither do any good. So before we get on to that, I just want to clarify in terms of information, when you'd use one or the other, what information is needed. So if we have a look here, it could be finding an angle or finding a side. So considering the sine rule first, if you're finding an angle, what you need to know as a bare minimum is an angle and a side opposite to it, plus as well just one more side or one more angle. So you need a pair of an angle and a side opposite to it, and you need to know both of those plus one other thing. To find a side using the sine rule, it's actually the exact same thing you need to know. You need to know again an angle and the side opposite to it, plus again just one more side or one more angle along with that angle and opposite side pair. For using the cosine rule, what do you need to find an angle? Well, this one's quite easy to remember. To use the cosine rule to find an angle, you need to know all the 3 sides. So that one's easy to spot. You can use the cosine rule if you know all 3 sides and nothing else. You can know more if you want, but the bare minimum is to know all 3 sides. Whereas if you want to find a side using the cosine rule, the minimum you need to know is an angle and the 2 sides that are either side of that angle. In other words, an angle and the 2 sides that enclose the angle. So knowing that, let's have a look and see which we'd use to solve this next triangle. So the first triangle you've got, triangle A, is this one. We need to find this angle x over here. So to find angle x, which is over here, have a look what we know. We know all 3 sides. So if I just remind you of the table, we know all 3 sides. We need to find an angle, and so what we'd be using here is the cosine rule for this one. So this would be a case where we need to use the cosine rule. We couldn't use the sine rule because we don't know an angle. So that one would have to be cosine and cosine only. For the second triangle, triangle B, again let's just think about what we know and also what we need to know, whether to use the sine and cosine rule. So just pulling up this table again, here's the table which tells us which one to use, whether it be the sine or the cosine rule. So just highlighting what we know this one's 14.4 and this side's 13.2, and we also know an angle in between 2 sides we know, and we're trying to find the side opposite. So if we have a look here for the cosine rule, if we know an angle, which we do, we know 30.6, and we've got the 2 sides which enclose that angle. The 2 sides which enclose 30.6 are the 14.4 and the 13.2. So we know 2 sides that enclose the angle, and so we can find this side using again the cosine rule. So like the first triangle, triangle A, triangle B is one where we'd again use the cosine rule. The third one, triangle C, again, let's just highlight and think about what we know and what we need to know, whether it be the sine or cosine rule. Here's a table yet again. So for this one, it would seem at first glance that we can't use either. We know two angles. It seems that we don't know an angle and side opposite to it, and so we can't use the sine rule, it would seem. But if you just think slightly carefully, it's a triangle, obviously. If we know two angles in a triangle, we can actually work out the other one. You know that, I don't doubt that you do. So 190 minus these other two will obviously give you this angle here. So if we just do this now, not that we need to as such, but just to show you, the angle I've just put here will be 180 minus 41.9 minus 65.9. This angle would be 72.2. And once you fill that one in, it becomes much more obvious, because now we have an angle and the side opposite to that angle. So this fulfills what we need for the sine rule. We know an angle and its opposite side, 72.2 and 11.2. Then we just need to know one more side or one more angle, which we do. In fact, we know two more angles. We could use sine if we just knew one more. And so this fulfills enough information for us to use the sine rule. So could we have used the cosine rule as well? Well, the cosine rule, we need it to find this angle, this side x here. To find a side using the cosine rule, we needed an angle and two other sides. We only knew one side, so no, we couldn't use the cosine rule. This one would be the sine rule only. And the last triangle for question 1, we need to know an angle, but we're not told any other angle, nor any other side apart from this one. So this one we can't use any, so we'd use neither here. Why? Because, quite obviously, there's just not enough information given in the question. So that's why we can't use either here. It's just completely useless for sine and cosine rule. Nothing would help us here unless we know more angles or more sides. Question 2 in this warm-up. We've got a right angled triangle here. So just putting information in, we know angle A is 90 degrees, that's a right angle. Angle ACB is theta, which we want to find. We know BC and we know AB. And so looking at this, we could have just used standard trig to find theta. So in fact, I'll do this now. Not that this is what the question's asking. The question's specifying that we need to use the sine rule. But just imagine that we wanted to just find theta in the standard way. We'd use sine because we know the opposite side, which is 13.6, and we know the hypotenuse, which is 19.1. So if you remember, you use the sine rule, you use the sine function if it's a right angled triangle when you're considering the opposite and hypotenuse. And so if we just do sine minus 1 of this, we can find theta. So therefore theta equals sine minus 1 of 13.6 divided by 19.1. So let's see what that gives us. So shift sine 13.6 over 19.1. We get to 3 sig figs, 45.4 degrees. But could we use a sine rule? Would we have got the same? Well, presumably we will, because it should give us a correct answer regardless of the method we use, as long as each method is obviously valid. So let's just commit this 45.4 to memory and remind ourselves of the sine rule now. So there's 2 general forms of the sine rule. one for finding angles, one for finding sides. You just need to remember one. You don't need to remember both. Essentially, one set is just the reciprocal of the other. So the bottom one is just these top fractions turned on their heads. So generally, for finding angles, we'd use this form here. So if we pick A, angle A as theta, we could write sine theta over the side opposite to that angle. So our A, if you like, is 13.6. Then we need another pair of angle and side. So we know these two here. We know that's 90 degrees, and that's 19.1. So sine theta over 13.6 is equal to sine 90 over 19.1. So therefore, theta will be inverse sine. If I multiplied this by 13.6 first of all, I'll just do this now just so you can see without me skipping too many steps. Sine theta would be 13.6 multiplied by sine 90 over 19.1. So we're just doing the inverse sine of this. So sine minus 1, 13.6 sine 90 over 19.1. And so if we just do this, we can just take what I had before and edit in sine 90. We indeed do get the same. And the reason for that is that sine 90 is just equal to exactly 1. That's why it works. So now we can move on and have a look at question 3. Question 3, we're actually using the same triangle as question 2, but now we're going to be using the cosine rule to find the side AC. So just to remind us of the triangle from before, here it is just sliding onto the screen. And again, it might seem to you that we could have just used Pythagoras to solve this, which indeed we could, but the point being is to show that the cosine rule is just an extension of Pythagoras to fit any type of triangle, whether it be right-angled or not. And so obviously AC, just using Pythagoras, would be the square root of 19.1 squared minus 13.6 squared. So if we just bash this onto our calculator and work out what it is, we've got 19.1 squared minus 13.6 squared, all of that square rooted, obviously, like I've said, to 3 sig figs 13.4. So we should get that when we use the cosine rule, like the question says. So just reminding you what the cosine rule is, it's a squared equals b squared plus c squared minus 2bc cos a. So you can see here, the side you want to know, a, if you like, depends on knowing the angle opposite to it, which is why it's a there. And so here, we want to know this side AC. So if I call this a, if you like, we need to know this angle here, which I'm just going to call big A. So obviously it would have been easy just to use Pythagoras. So if I just say here that we knew theta from before, where we worked out theta from question 2, and just remind you what theta actually was. So from question 2, theta was 45.4 to 3 significant figures. However, that wasn't exact. Because this isn't the final answer, it's always worth giving intermediate steps to more significant figures. And so theta here, just to write down the full working, we got theta by applying the sine rule. Theta was sine minus 1 13.6 sine 90. Sine 90 happens to be 1 anyway, but I'm just going to put it in as sine 90 anyway, over 19.1. And so to be more precise, it's 45.401. In fact, why not just give the full thing? 29247. This is just to make sure we're eliminating any possibility of rounding error. So now we know this is 45.40 and so on. We can work out this here by doing 180 minus 90 minus this. So if I just take this answer here and do 180 minus 90 minus that, just using the fact that angles in a triangle add up to 180, we see that this angle here must be 44.5987 and so on. .5987, what's the rest of it? 0753. So now we know A and the angle opposite to A, we can now apply the cosine rule. So, in other words, AC, which I've labelled as A in the diagram, is going to be the square root of all this here. So it's going to be the square root of b squared plus c squared, with these two are just the other two sides in any order. So 19.1 squared plus 13.6 squared minus 2 multiplied by these two sides in any order. So 2 multiply 19.1 multiply 13.6 multiplied by cos of angle big A, which we worked out here, was about 44.598 and so on. So I'll just say 44.59 dot dot dot, where the ellipsis just denotes that we're going to use a few more figures than what I've written down. And at this stage we can actually use the calculator to help, because it's got the angle stored in its memory here. And so if I just type in A and S, you can see that it's got it stored. So I'm just going to do square root of 19.1 squared plus 13.6 squared minus 2 multiplied by 19.1 multiplied by 13.6 multiplied by cos of the answer which is stored in the calculator, which is the angle. We get 13.4 centimetres, which is what we got much easier when just using Pythagoras. So this sort of proves, as it were, that the cosine rule is an extension of Pythagoras and can be applied to a triangle with any type of angle, not just a right angle. So now we've done the warm-up, let's now consider in a bit more depth the sine rule, which can be at times slightly trickier. However, before I start off talking about the sine rule as such, I just want to think about with you the graphs of y equals sine x, y equals cos x, and y equals tan x. In particular, I want to consider solving sine x, cos x, tan x being a certain value of y, where the value of x for sine x being equal to y is gamma, the solution of x for cos x equaling y is beta, and the solution for where tan x equals a certain value of y is gamma. This symbol here is a fancy looking y, but it's actually the Greek symbol gamma, which looks like y. This is beta, this is alpha. So just to give a bit more clarity in terms of what I'm saying, here's graphs of sine, cos and tan for you. The green one is a graph of tan x, the red one is a graph of sine x, and the blue one is a graph of cos x. These should be familiar to you to some extent from GCSE work. I'm going to mention some of the key properties and details about them as we go further into the lesson. But for now, I just want to consider what values of x would solve y equals tan x, y equals sine x, or y equals cos x. For example, if I was trying to solve it where y is somewhere in between -1 and 1, and so if I imagine y as a constant value and thinking what values of x would solve to give that value of y for the tan, sin and cos functions, you can see here, if I had a dotted line for a particular value of y, that actually there'd be many values, just picking on sine here for a moment, where sine of a certain value would give this value y, which is, I don't know, about 0.7. It doesn't matter, the actual value of y, as long as it's between -1 and 1, doesn't matter. For example, if x were here, you could see this value of x would yield a value of sine of that x being equal to this arbitrary value of y. But it wouldn't just be the only value of x we could take that would yield sine x equal to this y. We could take this one here, that value of x, it'd give the same value of sine x. This value of x would give the same value, as would this one, and so on as we go further down the line. That one, and so on. Now, I've only chosen x to go from about 720 degrees back to about -360. But if this line were extended to arbitrarily long lengths, there'd actually be an infinitude number of different values of x, which would yield the same value of sine x. And so, if I call these solutions here gamma, and just draw one a bit neater for you here, you can see here that actually just on this small portion of the number line we can see 6 different solutions that would give sine gamma equaling this particular value of y, which I've denoted by this dotted line. The same goes for tan as well. So you can see here tan would cross this dotted line here, and you have a look at the others, that's just one of them. You should see 5 others. And if I call these solutions here beta, for where tan beta equals this same value of y given by this dotted line, you should see the 6 solutions here. Similarly, for cos x, again you should see 6 points along the x-axis, which would give the same value for where cos of that value of x gives the same value for y, as is this dotted line. These points are here, and I've called these gamma. And so the sine, cos and tan functions are examples of functions which are many to 1. There's many different values of x which would give the same function value for where f of x is equal to the same value of y, where f of x might be the function sine, cos or tan. So let's link this back to an easier sort of function. So sine, cos and tan are the trigonometric functions. But what other function can you think of where there's more than one value of x which would give the same value of y? Well, I would suggest the function y equals x squared. For example, this one here. That's meant to say x squared. So we know that squaring an ordinary value gives a positive value. Therefore, the function f of x equals x squared sends, if you like, 2 different values of x to the same value. So, for example, -2 squared and 2 squared both produce 4. So let's just think about these trig functions here. So the trigonometric functions also actually behave in a similar way. So on your calculators, and you do this as well, let's work out the following. So what's sine 15? So let's just try this. So sine 15, root 6 minus root 2 over 4, that's an exact answer. So that's root 6 minus root 2 over 4. How about sine 165? So if I just go and edit this in and say 165, weirdly that gives exactly the same. So maybe that's just a fluke, who knows? So these two here give the same value. Let's try sine 20 now. So sine 20, what's this going to give us? Oops, never mind, just type it all in. Sine 20. That's 0.342. Let's just call it 0.342 to 3 sig figs. And how about sine 160? Well, sine 160, weird, that gives exactly the same value. So why would this be? So these two give the same value, and these two as well also give the same value. And so why on earth would that be? So just to ask the same question again about these, what do you notice? Well, obviously what we noticed here was that sine 15 is equal to sine 165, and also sine 20 equals sine 160. So what is the special relation in between this one and this one? So can you see it? Can you spot it? Well, I don't think it's too hard to spot, but if you're struggling seeing what's going on here, this one plus that one add up to 180. 20 plus 160 is 180. 15 plus 165 is 180. And in fact, it just so happens that generally speaking, if you take, say, sine of 165, that'll equal sine of 180 minus 165, which is 15. So generally speaking, there is a rule. So sine x is always the same as the sine of, in brackets, 180 minus x. So for example, in this case, x was 165, over here x was 160. You could pick a different value as well. For example, if you picked x was 40, sine 40 will be the same as sine 140. So don't take my word for it, check on your calculator. So sine 40 equals this, 0.643, whereas sine 140, again, like I say, will be the same. So in maths, if something can be easily proven without going too far off track, it's always best to prove it, I feel. So let's have a look at a nice geometric proof of this result, that sine x equals sine of 180 minus x. So let's prove the result. So anything I've done here is I've changed the x to a theta, just to clearly denote that we're talking about an angle. Theta is normally used for angles. So how would we prove that the sine of 180 minus theta is the same as the sine of theta? So what I'm going to do first of all is introduce a triangle. So diagram triangle ABC, where AB is W, BC is X, and the side AC is Y, and the angle here at A, I'm going to call that gamma. So we can do this step by step, and it's actually fairly easy to prove. So the first step is we need to write down the value of sine theta using this diagram. So just recalling from basic right-angled trig, sine theta, or sine gamma in this case, is the same as the opposite side divided by the hypotenuse. And so in this case, sine alpha will be x over y. And so we need to write that down and just store it for later use. So I'm just going to pop it here. Next, we come on to step 2. So step 2, create a triangle DBC by placing a point D between A and B, such that A, D and B are collinear. So A, D and B lie on the same straight line. So all we're going to do here is drop a straight line down using a ruler from C to a point somewhere in between A and B. So with a ruler, all you need to do is something like this. Okay, and you're going to label this point here D. So here's one I made earlier. The one I made earlier, put D over here. Doesn't matter whereabouts you put it. And then also, like the step says, we need to label on angle BDC. We're going to call this one theta. And the line from D to C, call that Z. So label it in carefully like I have done here. Your point D doesn't have to be here. It could be over here or there or anywhere really, as long as it's along the line from A to B. So once you've done that, the third step is we're going to use triangle DBC to write down the value of sine theta. So again, triangle DBC, this one here on the right hand side, is a right angled triangle again. So sine theta is the side opposite to theta, which is x, divided by the hypotenuse for this triangle, which in this case is z. So I'm just going to write this down over here next to what sine alpha was. And we're going to return to this later on. But for now, let's think about step 4. So step 4, write in terms of theta the angle ADC. So ADC is this one here. And this goes back to the very basics of GCSE. This is angles on a straight line. So ADB is a straight line. So if the angle at D is theta on this side, the other side of D, angle ADC, that must be 180 minus theta. So we can add this on like so. This then brings us to step 5. So step 5, in triangle ADC, this one on the left, we're going to use a sine rule to show that sine of 180 minus theta equals y sine alpha over z. And so if we apply the sine rule to ADC, what we've got first of all is angle 180 minus theta, and we also know the side opposite to this we've labelled as y. In the same way, this angle alpha here, the side opposite to that, is z. So using the sine rule, we can say that the sine of 180 minus theta divided by the side opposite to it, which is y, must equal the sine of alpha divided by the size of the side opposite to alpha, which is z. So therefore, if we just multiply both sides of this equation by y, we can quite easily see that the sine of 180 minus theta, if we multiply by y, we can put this y up here. So it becomes y sine alpha over z, which is exactly what we wanted to prove. We wanted to show this, and we have done here. So just one final piece to this puzzle, and then we've proven the result. So step 6, which I've just hidden down here, use previous results to show that sine 180 minus theta is equal to sine theta. And so what we need to do here is to prove that y sine theta over z is the same as sine theta. And so we've got sine theta here, which is x over z, but we know that x over y is sine alpha. So just borrowing this result here, we can rearrange to make x a subject. So we can say that x, just rearranging this one, is equal to y sine alpha. And so because of that, because x is equal to y sine alpha, we can substitute this into this I've highlighted in purple. So because of that, we can say that sine of 180 minus theta equals y sine alpha over z, but y sine alpha is x, like we've got here. So y sine alpha is the same as x. So I'm just going to substitute in here, but that's x over z, and then finally, what is x over z? Well, we can see that x over z is one and the same thing as sine theta. And that proves our result. So sine 180 minus theta equals this, which equals that, which we've shown is the same as saying it's equal to sine theta. So that proves the result which always holds true. The sine of 180 minus theta is one and the same as sine of theta itself. Now we need to consider the relevance of this result in terms of how it might affect how we tackle certain questions. And in fact it does on occasion affect questions involving the sine rule, because sometimes, not always, but sometimes there's a possibility for two solutions. So the sine rule can be ambiguous. So it all depends on reading the question very carefully. Sometimes a question will deliberately make it unclear, so you need to consider two cases. Or the question might make it clear so that you know you're finding one angle or the other. So I guess you might be thinking, what am I talking about? What two cases do I mean? So I'm going to explain here. So the previous result, that sine of 180 minus theta equals sine theta, it does sometimes cast out over the size of angles found using the sine rule. So just take, for example, sine 30. If sine 30 equals sine 150, which it does, then how would you know if an angle found to be 30 degrees isn't in fact 150? Because a sine of 30 is the same as sine 150, so both of these angles would actually fit with the sine rule. So how would you know if it's 30 or 150? And again, you might be thinking, well, you can just look at the triangle, and it's obvious if it's acute or obtuse. But what you will have seen from GCSE probably time and time again is the examiner's get out of jail free card, where they say diagram not drawn accurately or diagram not to scale. And so that's how they can legitimately justify you not just thinking it's one or the other. So sometimes you need to consider two different cases. And so to explain a bit better and a bit more detail why it's ambiguous, I just want you to think about this following image. So I've got a triangle here, ABC, and so I've colour-coded the angle A. So that angle at A is locked, if you like. And these two sides in red are fixed. And so this is a fixed angle, AB is a fixed length, and BC is a fixed length. And so if we had this angle here, A for angle, this side and that side, if we were given just an angle, a side next to it, then a side next to the other side, would that be sufficient to know that it must be exactly this triangle? Well, maybe it is this triangle, or maybe it could be used a different way. So keeping these lengths exactly the same, I could also have arranged this triangle ABC like this. That's also the same angle, that side's the same, and that side, which was here, I've just sort of moved that way, rotated about B, and it could go there. And so as you can see, this triangle here is completely different to this one here. And so angle, side, side, this case, is not the same as this, despite the fact that the angle does indeed look the same in this case. So for example, it could be a question where you told this angle A, you told these two sides, and you want to find angle B. So if you're wanting to find angle B, how do you know that the angle you're trying to find is this here, or if it's the bigger one? It might be acute, like this, or it might be obtuse. Same with angle C as well. If you're trying to find angle C, how do you know it's going to be this one here, which is clearly obtuse, or this one here, which is acute? I've got a little graphic as well which demonstrates this ambiguity a bit clearer as well, if I could actually speak clearly. Ambiguity is what I was trying to say. So point C could be here or there, C dashed, and it's quite nicely explained by this image. So C could be here, or C could be here, where I've labelled this one now D. So what I'm trying to say here is that you might know this angle at A, and you might also know the length AB, call that S, and BC, which is here, or BC dashed if it's in a different location. And you might want to be finding angle C here. So if you have a look at angle C, then like I've said before, it is ambiguous if we mean in this angle C here, or that angle C over there. They're clearly very different. So the angle C, or C dashed, may be obtuse or acute respectively. So it's helpful being aware of what you should have been taught at GCSE, tests for triangle congruency. So triangles are congruent if it's a right angle triangle, you know the hypotenuse and side. There's only one way that triangle could be made. If you know the triangle's all three sides, then if you know the side of one, and the three sides of a different triangle are the same, they've got to be the same triangle. Side angle side is also a test of triangle congruency, as is angle and a side in between another angle. However, angle, a side, then another side in that order, as is not sufficient for congruency. So you've got angle, side, side, don't make an ass of yourself. Maybe not very politically correct of me to say that phrase, but tends to stick in students' minds. So angle, side, side, just have a neon warning light there in your mind. Angle, side, side, it is ambiguous. There could be two possible answers for the angle you need to find. The best way, as ever with maths, of trying to get the concepts in your mind clearly is to do some practice. I'm going to show you a worked example with this. Right, so let's put this into practice. So we've got a task here of finding the missing angles x and y in triangle ABC. So all the information is included in the diagram to work with, and this is going to be one of those ambiguous cases. So, given that we know AB is 2.9, BC is 2.1, angle BAC is 40, we can use a sine rule to find the missing angles. ACB, the angle at C, which is x, and the angle ABC, the angle at B in other words, is y. However, finding angles using the sine rule, like I've said, requires extra care, as triangles without a right angle might contain an angle which is obtuse. So let's just consider the two possible cases carefully. So first of all here, let's just think about case 1, and let's work with the sine rule as we know it. So we need to find both angle x and angle y. So for case 1, let's just trust our calculators first of all. So case 1, sine x divided by the side opposite to it, which is 2.9, must equal sine 40 divided by the side opposite to 40, which is 2.1. So therefore, rearranging this, we get that x must be equal to sine minus 1, multiply both sides by 2.9 here, we get 2.9 sine 40 divided by 2.1, and let's see what that gives us. So shift sine 2.9 sine 40 all over 2.1. We get here to 3 sig figs, 62.6 degrees. So, case 1 might well be where x is equal to 62.6 degrees. Now, looking at this diagram, it would appear here that x is actually obtuse. Here we've got an answer which is acute. So for case 1, which is unlike what this diagram would have us believe, I'm going to say that case 1 is where x is acute. So let's just trust the calculator. So let's just say, for the sake of argument, let's say x is 62.6, and this just happens to be a really badly drawn triangle. So if x is 62.6, and this case is where x is acute, then y, just using the idea of angles in a triangle adding up to 180, y would have to be 180 minus 40 minus 62.6 to 3 sig figs. Y would equal, in this case, 77.4 degrees. Doesn't look like it. That looks very small. That looks about 20 or 30 degrees to me. But this is what we've got. And so how can that be the case? Does it say anywhere in this question that find the acute angle x or find x, comma, which is obtuse? No, it doesn't. Because the question doesn't say for definite if we're after an acute or obtuse angle, we have to consider both cases. In the same way with a quadratic formula, you have to consider both positive and negative values. You can't just go for one value using the formula. You need to think of both options. So that's one possibility right here. So why is it ambiguous? It's because, like I said before, we've got an angle here. Next to that angle, we know a side. And next to that side, we know a side. So angle, side, side, as is not sufficient for making and fixing a triangle that has to be identical. Angle, side, side. I could make another triangle with the same angle, followed by the same side length, followed by the other same side length, and it not be congruent to this one. For that reason, this is why this is only one of two possibilities. So the next case we're going to have a look at, case 2, is where x is obtuse. We've considered case 1, where x is acute. Let's now think about case 2, where x is obtuse. So it's not to say that the calculator can't be trusted. It's how you use it. But what comes out on a calculator to give an answer when you do sine minus 1, cos minus 1 or tan minus 1, what the calculator spits out at you is known as the principal value. Now the principal value might not even be a correct value in itself applied to whatever question you're talking about. Whatever the calculator gives you, that's called the principal value. So let's just consider case 2, x is obtuse, and start it out in the same way. So what we had was sine x over 2.9 equals sine 40 over 2.1. Rearrange this. Therefore x, just going to put in brackets now, the principal value just what the calculator happens to give us, which we're going to interpret in a moment. That's going to be sine minus 1 of 2.9 multiplied by sine 40 divided by 2.1 and that's going to give us, like we had before, 2 3 sig figs, 62.6. So that's the principal value. However, we're going with the idea that x is obtuse. So just remember the relation that sine theta is the same as sine of 180 minus theta. So what other value of x would have given us a sine of x which is equal to this? So what other value would have worked? So we can use this relation to help us. So because x is obtuse, that's going to imply that x is actually 180 minus this principal value, which would actually give us 117.4 degrees. To 1 decimal place. And therefore, y, in the case that x is obtuse, of course, would be 180 minus 40 minus this obtuse value of x, which should be 22.6 degrees, again to 1 decimal place. And so case 1, we had that x is 62.6, y is 77.4 if x were acute, or another possibility where x is obtuse, we have that x is 117.4 and that y is 22.6. I'm going to try and illustrate this now, and forgive me if I'm a bit rusty with my constructions on this software. I'm going to try and construct these two possibilities for you based off nothing more than information given in this question. What I'm going to do, just to try and illustrate to you how this could be the case where you've got two possible solutions for both x and y, is I'm going to actually draw it out using constructions like from GCSE. So we were told that the side of the triangle AB was 2.9, so I'm going to use this giant ruler here to actually just do AB. So from A to B was 2.9. 1, 2, 2.9 like so. We were also told that the angle at A was 40 degrees. And so I'm going to measure out 40 degrees. We weren't told the length AC though, so I'm just going to get my protractor, which I've hidden down here, bring it up, and measure out 40 degrees from point A. So popping it there, like so. 40 degrees. I'm going to do it in a dotted line, just to illustrate that it wasn't fixed, the length AC. So from here through 40, that's going to be a 40 degree angle, like so. I'll then just put this protractor down here for a moment. So if I just label in that this angle here is indeed 40 degrees, like angle A, then that's okay. We're also told that from C to B was 2.1. So from this point here, which is B, so this is A, whoops, so undo that. So this is B, and that's A. That's 2.1. So if I just get my virtual compass, then if it's 2.1, the side BC, then it's going to end, obviously, 2.1 centimeters away from point B. So if I just measure out 2.1 here, so I'm going to put the needle at 2.1 and stretch out, so that's now 2.1. I'm now going to draw in, again with a dotted line, all the points 2.1 centimeters away from point B. Like so. So now I can actually show you the possibilities for these two triangles. So I said here that that's point A down here. Oops. That's A. That's B. From A to B, we were told it's 2.9. And C is either going to be here or there. So that's one possibility for where C is. Another possibility for C is across here. So I could call it C1 or C2. In fact, yeah, I think I will just call it C1 or C2. I could have done C and C dashed. And so this here is angle Y. So let's call this Y1. That's one possibility for what Y1 is. And this bigger one here is Y2. Now we found the possibilities for Y to be 77.4 and 22.6. So if I've drawn this okay, this smaller option for Y, Y1, you should find to be about 22.6. So 10, 20, it's not far off, you know, that's not bad for me. You can see that's about 23 degrees, a bit less. So that one is about 22.6. And Y2 should be 77.4. So that's 70, 75, 76. It's about 77, so I'm a bit off there. But hopefully that shows you why it actually has to be considered, these two cases. So that's 2.1. And likewise, this side here is also 2.1. I could have also done it by measuring the sides as well. If I measured the sides, I'd get a different length for AC1 as I would for AC2. So that's something else you can actually try yourself if you've brought your compass and protractor to an A-level maths class, which I very much doubt you have. You wouldn't ask me to do this in an exam, by the way. You'd never be asked to use compass and protractor to do constructions for A-level, but it's just handy showing that it all links in from GCSE right the way up. So it's all still relevant, even if in a smaller way. So now we're going to do a worked example before you try some of these question types yourself. So this is a case of the ambiguous sine rule. So first of all, in this question, we're told some dimensions of this triangle ABC. We're told it's got a side AC which is 7.2, a side BC which is 5.4, and an angle BAC which is 40 degrees. So the best thing I'd suggest to do now would be just to sketch out the triangle without any worry about how accurate your sketch is. So just to sketch it out sort of any old how, I'll put a side here. Second side can go up like so, and then one coming down like this. So we're told it's triangle ABC, so just draw on A, B and C in any order. We're then told that AC is 7.2, so I'm just going to label this 7.2 like so. BC we're told is 5.4, so I'll call that 5.4. And the angle at A is 40 degrees. So I'm just going to label that like so. Then we can think about part A and part B to this question. So for part A, we need to find the two possible lengths of AB, and for part B, we need to find the greatest possible value of the angle ACB. Now I'm actually going to start off by considering part B right here. So part B, let's just bring up our sketch from before, like so. So we need to find angle at C. Whoops, no. Yes, we do. Angle at C, which is up here. So there's two different cases to consider because this is going to be one of these ambiguous sine rule type questions. So I'm just going to branch off and make sure I don't go into this diagram here. So I'm just going to corner this off like such. So first of all, if I just call this one down here as theta, I'm not going to work this out directly because I don't know this angle and I don't know the side opposite to it. Whereas if I call this angle here theta, then I know this one, well I don't know this one, what I mean to say is I know the side opposite to it, and as well as that I know 5.4, and the angle that's opposite to, which is 40. So just considering this angle here at B in the first instance, we can say that sine theta over 7.2 must equal sine 40 over 5.4. So therefore, working out the principal value of theta, theta is going to be sine minus 1 of 7.2 multiplied by sine 40 all over 5.4. So just using the calculator to work out what this is going to be, so if we do shift sine 7.2 sine 40, close brackets, all over 5.4, then that comes out to be 58.9 and so on. So I'm going to give this to a few more decimal places than before, because this isn't the final answer. This isn't the angle we're actually wanting to find. So this is like an intermediate step. So give it to more than 3 sig figs. I'd say give it to double that at least. Give it to 6 sig figs to avoid any rounding error. So I'm going to write this as 58.9869, then I'll call that 7. So that here is one option. So theta might be 58.98697, and that here, just to remind you, that's called the principal value. So that's one option where theta is acute. Based on my sketch, theta looks obtuse, which is linking back to this case being ambiguous. And remember, what we know is angle, then side, ASS, alarm bells should ring. This is why we have the ambiguous case. So when 58.98 and such, that's a principal value. But if you have a look what Part B asks us for, Part B asks us for the greatest possible value of ACB. We then need to remember that sine of 180 minus theta is the same as sine theta, that identity that we proved before. So therefore, the greatest possible value of theta is 180 minus this 58.9 odd, 98697 blah blah blah. So I'm just going to do 180 minus this on the calculator. We get 121.0130. That'll be accurate enough. So 121.0130. But of course, that isn't what we wanted to find. We're after the angle at C. We found two possibilities for theta, which are these two. But what we're actually wanting is the angle ACB, which is this one here. So the greatest possible value of C, so the greatest value of ACB will actually be when theta is at its smallest. So it'll be 180 minus the 40 minus the smaller value of theta, which is this 58.9 whatever. And that comes out as 3 sig figs to be 81.0 degrees. So that's the greatest possible value of ACB. It's not the only possible value, but it is the greatest possible value. We have, however, answered the question. So the greatest possible value of ACB is 81.0 degrees. Looking at part A though, it asks us to find two possible lengths of AB. Okay, so for AB, this one down here, it depends on what option for C we're going for. Okay, so the greatest option for C is 81.0, but there is also another case. I'm going to call the first case just case 1. I'm going to call case 1, which is where ACB is at its least value. So where ACB is at its least, then ACB may well have been 180 minus 40 minus the greatest value of theta here. So it might have been minus 121.0130. So it might have been the case that ACB was actually 19.0 degrees, if you want to be not too accurate about it. To be more accurate with this calculation, what I'd suggest we do is to use the direct and exact option. So put in as many numbers as you can into this. So 180 minus 40 minus 121.0130. Let's just check this here. So we've got this here stored, luckily. So 180 minus 40 minus the greatest possible option for theta, which was for 121.0 and such. It could be that the angle at C was actually 18.98696 and such. So I'm just going to write this as 18.986. What are the other numbers I've forgotten? 986 can't read. 969. So 96953. Okay, so I'm just going to show you a sketch of this, just so it adds a bit more dimension to the proceedings. So here it is. So imagining that the case where angle at C is 18.98697, then using this particular case, we could work out the length of AB by again using the sine rule with this particular case. So what we'd have here, if I just call AB as X, I'm lacking imagination today, so I'll just call this X. Then we can say that X over sine 18.98 ... because obviously it's quite a long awkward number. That equals one of these sides over the sine of an angle we do know. And so what I'm going to go for here, because you know that A is 40, that's probably the easiest one to know and to use. So I'm going to say that's the same as 5.4 over sine 40. So in this case, this can be rearranged so that X equals 5.4 multiplied by sine 18.98, so on and so forth, divided by sine 40. So if we use a calculator to work this one out, so I've got this number stored perfectly, so that's stored as the answer. So answer, got this angle here, and so 5.4 sine of that stored value, all divided by the sine of 40. That gives us an answer to 3 sig figs of 2.73 centimetres. And so from that we can say that AB is 2.73 centimetres. Or it could be the second case. That's case 1. Case 2 is where ACB is at its greatest. And so ACB, where it's at its greatest, was 81.0 degrees. So to be more accurate than 81.0, it was 81.01303. So I'll just say case 2. Angle ACB. So at its greatest. then we can employ the same idea here to work out what AB is, which again I'm just going to call x. So x over sine, this time of this value, so 81.0 and so on, that's going to equal 5.4 over sine 40, because that 40-degree angle is locked in. That's what the question tells us this angle is. That's 40 degrees all the time. So in the same way as before, just rearranging this to find x, for this case, we have that x would be 5.4 multiplied by sine of 81.01303 all over sine 40. So let's just work this out on the calculator. So same idea, but instead of sine of the previous angle, it's now 81.01303. So given that to 3 sig figs, that comes out at 8.30 centimeters. So again, if you're interested to see how that works in reality, not that you'd ever need to construct the two possible options, here they are. So first one, where C is only 19.0, the bigger option is where it's 81.0, and the bigger angle corresponds to the side AB being 8.30. The smaller angle for C of 19.0 obviously corresponds to the smaller side length of 2.73. Here, the side BC could go here, or imagine this being the compass needle and it's swiveling around along this arc. B could have been over here, which I've called B dashed. So now it's over to you to try out some questions on this. So if you could turn to page 184, exercise 9C in the blue algebra book, try questions 2, questions 3 and question 6. So again, this lesson has been quite a hard slog in terms of explaining it, but it is a crucial concept that you understand well. So try those 3 questions, let me know if you're getting stuck, check your solutions using the answers at the back of the book, and keep plugging away. So be in touch with me if you can, please, and I'll see you soon, I hope. Thanks again, and see you all soon.